Okay, well, it's my pleasure to welcome you back to the session, and our first speaker is Mina Aganagic from UC Berkeley. Her second talk on knot categorification from mirror symmetry.
Okay, well, thank you all for joining. Let's see if I can change the slides. All right, so now I'll describe how to get homological link invariance from this hyperkähler manifold that featured in the last talk. The manifold is the moduli space of monopoles in R3, singular monopoles in R3. So in this first lecture, we understood the geometric origin of basic structures in conformal field theory of fusion and braiding from perspective of the derived category of T equivariant coherent sheaves on X, or simply the category of B-type branes, equivariant B-type branes. So what we saw that the analog of the conformal field theory statement that fusion diagonalizes braiding is existence of a perverse filtration in the sense of Roque and Chuang, who's near a wall in Kähler moduli that corresponds to bringing a pair of vertex operators together. So the terms in this filtration are labeled by the fusion product, and the special feature of the filtration is that it's preserved by the action of braiding, and braiding acts in a very rigid way on it. It essentially acts on the quotient subcategory just by degree shift. So that's as close as you can get to diagonalizing the action of braiding on the derived category. Now, we'd like to understand, we did all this to understand, in part to understand what fusion is, but also to understand what objects of the derived category correspond to caps and cups. Now, a cap colored by representation by V, which recall all our representations are minuscule, comes from a pair of vertex operators colored by V and its conjugate, which approach each other and fuse to identity. This is how you get this picture, because identity is no insertion. The objects of the derived category that correspond to such conformal blocks necessarily belong to the lowest term in the filtration. That's the lowest, because the associated representation is the lowest representation you can get in the tensor product of V and V star. Because, so in general, any object at any other order in the filtration will mix up with objects from the lower orders. Since the objects associated to caps necessarily live in the lowest term of the filtration, this has nothing to mix up with. So they're necessarily eigenshifts of the braiding factor. So on them, braiding has to act only by degree shifts. And moreover, it acts by the degree shifts which we computed from conformal field theory. Okay. More precisely, the equivariant degree shift essentially comes from conformal field theory. There is a subtlety there that is associated with some overall normalization. That natural normalization that conformal field theory gives you is not entirely the natural one that that braiding gives. There's some overall shift that I explained in the paper. But anyhow, and a shift by the dimension of the vanishing cycle, which is an integer that we also were able to understand from just from the close relation of central charges and equivariant central charges to conformal blocks. That integer is just the dimension of the vanishing cycle. So the fact that braiding that changes the orientation of the cycle changes the cohomological degree, which is what's in the brackets, in the square brackets, by the dimension of the cycle is the natural thing. Now, this will happen anytime. So any brane at the lowest order of any such filtration we get will always be an eigensheaf of braiding. However, at the corresponding wall only. However, the kind of braiding that you get near a wall associated to bring conjugate representations together is very, very special, because the identity representation is very special. Okay. So we'll see things that we won't see generally at lowest orders in the filtration. So in this case, the relevant part of the geometry of X is a cotangent bundle to a minuscule Grassmannian, and the minuscule Grassmannian. I don't quite have enough time to review all the notation from last time. Hopefully you can look back, but it's a minuscule Grassmannian whose so P here is the maximal parabolic subgroup of G associated to the minuscule representation B. Okay. This is just a very well-known calculation, and that shows that this particular monopole modular space is a cotangent bundle to a minuscule Grassmannian. You can find it, for example, in literature on Langlands correspondence. Now, when a collection, so now more generally, we don't want just one cap, we want several caps because we want to use these to close knots eventually. So we want to bring together vertex operators in pairs colored by complex conjugate minuscule representation. When we do that, our manifold has a local neighborhood where we can approximate it as a cotangent bundle to a product of minuscule Grassmannians associated to representations that come together. So correspondingly, we got a very special B-type brane, which is simply the structure sheaf of this vanishing cycle. Among other things, this very special brane is its vertex function, its J function, is the conformal block that corresponds to this picture. Now, so when we use this, the homes between such branes with the action of the braiding functor should, well, the Euler characteristic per construction is a not invariant. It's per construction the not invariant because as we explained last time, the Euler characters of this theory manifestly categorify the braiding matrix elements. Okay. So in addition to the Euler characteristic giving you the link invariant, we also know that the homology group is manifestly braid invariant as well. So it's invariant under the corresponding moves that you're just changing the braid presentation. Using very special, now we would like to say more. We'd like to say that more is true, that in addition, the homological, the homology group is actually a link invariant, itself a link invariant. Okay, that we don't know yet. Okay, using very special properties of these perverse filtrations and the vanishing cycle branes, it's actually not difficult to show that not only do homology groups categorify the link invariant, they are themselves link invariant. To show this, what we need to do is we need to show that the following relations hold: a version of the pitchfork identity, something called an S move or Reidemeister 0, and a frame Reidemeister 1 move. The fact that it's a braid invariant is Reidemeister 2 and 3, which we already know. So for all of these, in conformal field theory, purely, one would like to view the cap as a map between the space of conformal blocks with n-1 vertex operators and the space of conformal blocks obtained by pair creation, viewing this cap as a pair creation process. So this pair creation has the inverse process where a pair of vertex operators come together and disappear, which gives you the cap. Now, the fact that these maps in conformal field theory satisfies the three relations we just named follows from properties of fusion and braiding in conformal field theory. The fact that they hold is something one can prove, and it's the algebraic reason why conformal field theory gives rise to link invariance. It's obvious from transhymous theory perspective. It's not obvious from conformal field theory perspective. Okay. Yet it has to be true, and indeed one can prove that it's true. Now, from the geometric perspective, these maps between spaces of conformal blocks originate from functors between derived categories, the cap and the cup functors. These functors are defined in a standard way using Fourier-Mukai kernel, which is a structure sheaf of with respect to a structure sheaf of a holomorphic Lagrangian on the product of the from manifold to the to manifold, which is used to identify objects and morphisms between them. It's essentially a prescription of how to identify the incoming and the outgoing manifold. The existence now, in general, proving that Fourier-Mukai kernels satisfy these relations is hard work. You can see examples of such work. For example, the works of Kamnitzer and Kautis, which use the closely related but different geometry. Okay. The existence of this perverse filtration on the derived category, however, simplifies such proofs dramatically. Okay, and in a way provides an a priori understanding why such relations should hold in the derived category. So let me sketch how this works. So, for example, to prove this relation, the relation is a statement that the composition of functors on the left and the right are equivalent. So where the two C's are the cap functors on the left and on the right, and B is the braiding functor that corresponds to doing this braiding. Okay, and it's the braiding functor that braids one vertex operators with a pair. Okay. Now we can identify the images of the two cup functors as bottom parts of double filtrations that the derived categories develop near an intersection of a pair of walls, because now we are bringing three vertex operators together. So we are near intersection of a pair of walls. The braiding functor acts on the bottom parts of these double filtrations only by degree shifts. These are trivial in our case because if they weren't, the relations we are trying to prove wouldn't hold even in conformal field theory. So now the functor that acts only by degree shifts, all of which are trivial, is an identity functor. So one finds the equivalence of this. And others follow in a similar way. Another it's a very elementary but nice consequence is a simple geometric explanation of mirror symmetry of link invariance. So mirror symmetry for link invariance, is the statement that invariance of a link and its mirror image are simply related by inverting the variable q of Notch invariance. For us, this follows from Serre duality, which is an isomorphism of q cohomologies with branes f and g, no matter what they are, at the two ends, and the q cohomology obtained by reflection that exchanges the two endpoints. This comes with a shift in not just in cohomological degree, which is the usual thing, but also equivariant degree, because while the canonical line bundle of X is trivial, its unique holomorphic section is not invariant in scales under the C star action, corresponding to Q. And simply taking the equivariant Euler characteristic on both sides, and using the definition, one finds the mirror symmetry relation. The fact that Serre duality implies mirror symmetry is not an accident. In fact, it's built in from the outset, because the direction along the interval and along the link which get reflected coincide. Now, recently, Ben Webster proved that link invariants that come from Rx and B-type branes, the category of B-type branes on it, in the way I described, are equivalent to the invariants that he himself derived defined in 2013, purely algebraically in terms of KRLW algebras, studied by Kovanov, Lauda, by Roque, and himself. And this geometric description that I provided not only reproduces what he had, but also improves the understanding of the caps and the caps in the theory. Moreover, as I said earlier, the story extends to links in R2 times S1, not just links in R3, and gives homological invariance of links in R2 times S1. So we're getting more. However, as stated, neither the approach by the derived category of coherent sheaves on X, nor by the KRLW algebras is very computation friendly, at least not to my eye, not to my eye. And I think that is generally known. Basically, the approaches by KRLW algebras can reproduce what's already known, but they don't give you, they're not, you can't really get new homological invariance from them at the moment that you don't know by some other means. So in what follows, I'll describe how to reformulate the problem and get a much simpler description. So the second description is based on a Landau-Ginzburg model, which is the equivariant mirror of the manifold X that featured so far. Ordinary, so since X is hyperkähler, ordinary non-equivariant mirror of X is to a first approximation given by hyperkähler rotation of X. It's true to a first approximation, but not exactly. The manifold Y is, if X is the moduli of monopoles in R3, Y is related to moduli of monopoles in R2 times S1. It's what's called a multiplicative version of X. Anyway, but that, now as X has only kähler, but no complex moduli because of the T equivariance we impose, because we took all the singular monopoles to be at the origin of this complex plane C in R3. Y has only complex but no kähler moduli turn on. A description based on Y would give a symplectic geometry approach to the knot categorification problem with the derived category of X replaced by its homological mirror, an equivalent category, derived category of appropriate Lagrangian branes on Y. Okay. This is not what we'll do. So this should give us something equivalent to what we essentially already have. Okay. We'll do something different. We'll take advantage of the fact that because we're working equivariantly with respect to the C star action on X that scales this holomorphic symplectic form, all the relevant information about the geometry of X is contained in the locus preserved by this action. The locus preserved by this action, the best way to think about it is as, so if X we started out with is the moduli space of monopoles on R3, the locus preserved by the C star action, the locus we want to work with is the locus in the modular space of monopoles where all the monopoles, singular or not, are at the origin of C and at points in R. This locus is a holomorphic Lagrangian in X, which we'll call its core. So now we have a notational problem, which is that we have two different X's, which look different but sound the same. So I'll call the original X, the big X, and call its core the small x, because the big X is, the dimension of the big X is twice that of the small x. So again, a small x is the modular space of where is the Lagrangian in the modular space of monopoles, holomorphic Lagrangian in the modular space of monopoles, where all monopoles are at the origin of C and at arbitrary points in the remaining line. What we'll define to be the equivariant mirror of the big X is a manifold which we'll call Y, which is the ordinary mirror of its core. So we have a pair of mirror symmetries, one relating the big X to its mirror, the big Y, and another relating the small x to its mirror, the small y. And what I call equivariant mirror symmetry is the relation going diagonally. Now, while the small x embeds into big as a holomorphic Lagrangian submanifold, the big Y fibers over the small y with holomorphic Lagrangian C star fibers. So the bottom row here has as much information about the geometry as the top, because it has to have as much information about the geometry as the top, because we're working equivariantly with respect to the section. While they contain the same information, working downstairs as opposed to upstairs will turn out to have many advantages, which will slowly become manifest. A model example to keep in mind is the big X, which is the resolution of an AM-1 surface singularity. That big X is the moduli space of a single smooth SO3 monopole in presence of M singular ones. For that X, which is familiar from other contexts, not just as a modular space of monopoles, its core looks like a collection of M-1 P1s with a pair of infinite disks attached. The ordinary mirror of the big X is the big Y, which is a complex structure deformation of the multiplicative AM-1 surface singularity with some potential that we won't need. This multiplicative AM-1 surface singularity is a C star fibration over Y, which looks like an infinite cylinder with M mark points in the interior. And at these mark points, the C star fibers of the big Y over small degenerate. So you'll notice that Y is a single copy of the Riemann surface where conformal blocks live. And the positions of punctures of vertex operators is exactly where the C star fibration degenerates. What we'll use later is that there are M-1 Lagrangian spheres in the big Y, which are mirror to the M-1 vanishing P1s in the big X. They project to Lagrangians in the small y that begin and end in the punctures like this. Now, by SYZ mirror symmetry, the small x and the small y share a common base, which is simply a real line with M marked points. It's a moduli space of one smooth SO3 monopole on the real line in presence of M singular ones. So just forgetting about the circle on each side, we get this picture. More generally, the equivariant mirror of the big X and the ordinary mirror of its core is Y, which is roughly the symmetric product of copies of the Riemann surface with punctures where conformal blocks live, with some locus deleted. To first approximation, this map pi can be ignored. The symmetrizations, so we have a product of symmetric products, one for each simple root. They come from identifying the smooth monopoles whose with the same charge, their charge being a simple root. Projecting to the common SYZ base of the small x and the small y is the same as projecting the big X, which starts out as the modular space of monopoles in R3, just to a modular space of monopoles on the real line. Okay. That's why we're getting these symmetric products everywhere. Including the equivariant T action on the big X and the small x corresponds to adding to the sigma model on Y a potential that is a multi-valued holomorphic function on Y. So it's a sum of terms. The W0 term in the potential is mirror to the equivariant action that provides the variable Q. W0 is a logarithm of a function f naught, which written in terms of, well, we are working on a symmetric product of copies of the Riemann surface. So in terms of coordinates coming from viewing the Riemann surface as a punctured complex plane with 0 and infinity deleted is given by the following formula. Okay. Notice that F has zeros whenever any smooth monopole hits a singular one, or when any pair of smooth monopoles of the same kind, and poles when any pair of the smooth monopoles of the same kind collide. And there are additional zeros associated with links in the thinking diagram. Anyway, thinking of the big X as the Coulomb branch of a three-dimensional. Remember, there was another way of to think about the big X. In addition to thinking of it as modular space of monopoles or resolution of some transversal slice in defined Grassmannian, we could think of it as a Coulomb branch of a 3D gauge theory. From that perspective, this W0 term in the potential is associated with integrating our charge matter. I will explain this connection to why this connection to the 3D gauge theories exists in the first place, and how to derive this potential from that perspective in the last lecture. The divisor F0 that we need to remove is the locus of zeros and poles of the holomorphic function. Remember, W, the potential, is the logarithm of it. So to define W0, we need to remove from a manifold places where F naught can become either 0 or infinity. The other terms in the potential are mirrored to the lambda action that preserves the holomorphic symplectic form on the big X. In terms of Transhymus theory in R2 times S1, the corresponding parameters lambda rank G, worth of them, are the conjugacy classes of the holonomy around the circle of the Transhymus gauge field. Now, because y is 0 and infinity are already deleted from the Riemann surface, we don't need to delete any additional loci for the other terms in the potential to be defined. They're already defined for us. And thinking of X as the Coulomb branch of a 3D gauge theory, these additional terms in the potential turn out to come from Fidel-Laplace terms. The symplectic form on the small y is inherited from the big Y by restricting to vanishing S1 fibers in each total torus fiber over Y. And both the big Y and the small y are certainly the big Y is a smooth, exact symplectic manifold because it's essentially just a hyperkähler rotation of the big X that's also smooth. And the small y should be smooth as well. The Kähler form inherited from the big Y should provide a sequence of blowups that resolve intersections between irreducible components of F naught in the symmetric product, so which one can partially verify. Okay. These blowups don't introduce any additional parameters because the loci being blown up are also places where you delete which pass through F naught. The complex geometry changes, but you don't introduce additional parameters. And in particular, don't spoil exactness. Finally, twice the first Chern class of Y vanishes, which is important because what this means is that we can define the B model on Y with potential W. This topological B model on Y with potential W, we'll see momentarily, as mirrored to the A model on the big X. Topological A model on the big X, closed topological A model on the big X. And it also will allow us to define a category of A-type rings with a Z grading associated to fermion number. Now, from mirror perspective, conformal blocks are partition functions of the B-twisted theory on this very long cigar with an A-type boundary condition and infinity corresponding to choice of a Lagrangian in Y. Such amplitudes have the following form, where omega is the top holomorphic form on Y, the section of the canonical bundle. W is the Landau-Gisbert potential, and phi is a chiral ring apparatus. This reproduces integral formulation of conformal blocks of the affine Lie algebra, which goes back to works of Fagin and Frankel in the 80s, and also Schechtman and Varchikov. So we understand it here as a consequence of mirror symmetry. The fact that the case equation that the Landau-Gisbert integral solves is also the quantum differential equation of X, gives Giventhal type proof of two-dimensional mirror symmetry at genus 0, relating the T equivariant A model on the big X and the B model on Y with potential W. Now, one of the harder problems in studying Landau-Gisbert models is identifying the flat coordinates on the moduli space in terms of which these cigar amplitudes satisfy a simple set of holomorphic relations, where C is a multiplication by derivatives of the by operators obtained as derivatives of the potential with respect to the flat coordinates, and you're taking ordinary derivatives. In the Landau-Gisbert model, these flat coordinates are obtained by solving, as explained by in the old paper by Cicciotti and Vaffa, obtained by solving a coupled set of equations for the coordinates themselves and also the operators phi and sigma. In the present case, these flat coordinates. Now, in fact, a general way to produce such flat coordinates is mirror symmetry. So in our case, mirror symmetry identify, or these flat coordinates either by mirror symmetry or simply by direct computation are the relative positions of vertex operators on the Riemann surface that enter the Landau-Gisbert potential. And the equation that the cigar amplitude satisfies is just exactly is the case equation. There's a reconstruction theory due to Giventhal and Telemann, which says that starting with the solution of the quantum differential equation, one gets to reconstruct all genus topological string amplitudes of any semi-simple two-dimensional field theory, any massive two-dimensional field theory. So it follows that from the theorems that the B-twisted Landau-Gisbert model on Y with potential W and the A-twisted sigma model on the big X working equivariantly with respect to T are equivalent to all genus. So even though the dimensions are different, the topological string amplitudes, closed topological string amplitudes are the same. So equivariant mirror symmetry holds at the level of equivalence of topological string amplitudes. I didn't explain what it means at the level of homological mirror symmetry, and we'll understand this in due course. So now, corresponding to a solution of the Casey equation is an A-brane at the boundary of this long cigar at infinity. This brane is an object of the category of A-branes, which is the derived Fukaya-Seidel category of Y with potential W. The object of the derived Fukaya-Seidel category are simply graded Lagrangians on Y. The grading is what's needed to define cohomological and equivariant degrees of both the objects and the morphisms between them. The cohomological grading or fermion number Maslov grading is familiar. It arises, it's defined, for Lagrangian, is defined by choosing a lift of the phase of the square of the holomorphic form to a real valued function on the Lagrangian. So the A-brane is a Lagrangian L together with the choice of this lift, a graded A-brane, graded by Maslov grading. So the brane obtained from a given choice of the lift by changing the lift by 2 pi I times an integer is the brane that differs from L by cohomological degree shift. Now, in our case, this derived Fukaya-Seidel category should be thought of as a category of equivariant A-branes because of the fact that W is multivalued. The equivariant gradings come from a collection of one forms that Y has. One forms with integer periods that are related to the potential by as follows. Okay, the fact that these one forms, this doesn't work very well. The fact that the one form associated to lambdas are there simply follows from the fact that the target is a symmetric product, essentially symmetric product of cylinders. The fact that this one form exists is because we deleted from Y this locus F naught. The equivariant grading of a Lagrangian is defined analogously to the Maslow as the Maslow grading. Is the choice of a lift of phase of e to the minus the Landau-Gisbert potential to a real valued function of the Lagrangians, well, assuming lambdas are real, similar to what we do for the Maslow gradings. And changing the lift is a equivariant degree shift operation. The changing of the lift, remember W has logarithmic, it involves a bunch of logarithms, and changing the branch of the logarithms shifts the W like this. That shift is the change of the lift of W and the shift in equivariant grading of the Lagrangian. The spaces of morphisms between a pair of branes is simply the space of supersymmetric ground states. Or the cohomology of the supercharged Q of the theory in an interval with a pair of A branes as boundary conditions in parallel to what we had on the B side. These spaces of morphisms or supersymmetric ground states are defined in this case by flow theory, which is modeled after most year approach to supersymmetric quantum mechanics. The starting point is the Floor complex, which is the vector space of perturbative ground states spanned by intersection points of the two Lagrangians and graded by cohomological or Maslov and equivariant degrees. This vector space becomes a complex because of the action of a differential obtained by counting holomorphic disk instantons, which map the incoming end of the strip to an intersection point P, the outgoing end to P prime, and which have cohomological or Maslov degree 1 and equivariant degree 0. The condition that equivariant degree of the map is 0 means that the periods of all the one forms around its boundary vanish. That condition is the same as the map simply being in Y. It means these divisors which we are deleting don't pierce it. Alternatively, it's the condition that W is a regular function on the disk, pulls back to a regular function on the disk. So the actual space of morphisms or supersymmetric ground states is the cohomology of this complex. It's known as the Floor cohomology. Now, the way this comes about is somewhat non-trivial and goes as follows. The theory on the strip can be described as supersymmetric quantum mechanics with an infinite dimensional target space, which is the space of maps from an interval to Y, obeying the boundary conditions, with a real potential, which is dysfunctional. This is explained in the works of Iqbal, Hori, and Vafa, and Gayota, Moore, and Witten. The space of perturbative ground states is simply the space of critical points of this potential. The critical point equations are what Gayota, Moore, and Witten called soliton equations. Here, X is the vector field on Y generated by a Hamiltonian, which is just the real part of W. And the equations have to solve the boundary conditions. The solutions to these equations are simply paths which are time one flows of the Hamiltonian, the real part of the given by the real part of W, which starts somewhere on L0 and ends somewhere on L1. Now, finding such paths is the same as finding intersection points of L1, not with L0, but with the Lagrangian obtained from L0 by time one flow of the Hamiltonian, because these produce the initial conditions for the flows. Now, a crucial aspect of the Fukaya-Seidel theory, or the A model, is invariance on the deformation of its Lagrangians under arbitrary Hamiltonian cyclic dimorphisms. This allows us to undo the deformation from L0 by this Hamiltonian flow to get a Floral complex that's simply generated by intersection points of Lagrangians that we started out with. This means that the theory is essentially independent of W. That reflects the fact in supersymmetric quantum mechanics that the cohomology of the supercharge Q is independent of the potential, changing the potential by some amount, X by conjugation. So Q and the operator you get by conjugation have the same cohomology. More precisely, cohomology, and this is important, cohomology remains invariant as long as the perturbation does not result in any states coming in or going to infinity. This is the case if the Lagrangians we consider compact. Then the intersection points, or at least one of them is compact. Then the intersection points can't run off to infinity. And the theory would be entirely independent of the potential were it single valued. The Lagrangians that we really need to get not invariants are all compact. Because they're in particular, they're related by mirror symmetry or equivariant mirror symmetry to Lagrange, to branes on the big X, which are certainly compact. Now, for such compact branes, the only effect of a non-single valued potential such as ours is to introduce equivariant gradings. So, for example, an intersection point of a pair of Lagrangians at which W agrees, the W's on L and L1 agree for some choice of grading N of L1 has equivariant grading N. And it's defined to be the generator of the Floral complex between L0 and L1 in degree N. Okay, so essentially all of our generators of Floral complexes and cohomologies have the graded Euler characteristic of the theory, so picking any gradings, the graded Euler characteristic is we don't want to lose any intersection points between Lagrangians. So we will not, so picking L0 and L1, what you don't want to do is consider homology only in equivariant degree 0, because you're going to lose essentially all the intersection points. So what you do instead, just as you do for the fermion number, will sum over all homological degrees. So in that sense, all the terms on the right-hand side, each term individually has degree 0. Okay. Anyway, so the graded Euler characteristic simply computes the equivariant intersection number of the Lagrangians, where the usual intersection number is refined by keeping track of equivariant degrees. The differential is the first in a sequence of maps, which one gets by taking the domain to have k incoming strips and 1 outgoing, and which map in Y to intersection points of Lagrangians as follows. The maps that contribute to the kth massive product have Maslov index of fermion number 2 minus k and equivariant degree 0, just for the map to be in Y. Now, of particular importance is the second of these, the second massive product, because it gives rise to a product of morphisms on the derived category, which is an associative product on Floral cohomology groups. So it descends to an associative product on Floral cohomology groups. The fact that you get a product on cohomology and not just on chain complexes is a consequence of A infinity relations. And in particular, because for k is equal to 2, Maslov index is 0, only maps of Maslov index 0 and equivariant degree 0 contribute to the product. So the products preserve the degrees. Now, working with a derived Fukaya-Seidel category as opposed to the Fukaya-Seidel category itself is actually simpler. The derived category has far fewer objects. Instead of simply saying that branes related by Hamiltonian isotopies of individual branes are equivalent, we'll say that any deformation of branes that does not change the amplitudes is an equivalence. So which is a far larger symmetry. For example, starting from a pair of branes that intersect transversely over some intersection point, we can get, and with orientations chosen so that the intersection point corresponds to a Maslov index 0 home from L0 to L1, we can get a new brane, which is a connected sum of L1 with L0 with in grading shifted by 1 or orientation flip, obtained by gluing them together at the corresponding point. So it's taking connected sum. The differential acting on the chain complex from that brane, from any brane to that brane, is then simply the Floor differential. The connected sum brane is equivalent as the object of the derived category to a complex, which stands for taking the direct sum of L1 with L0 in degree 1 and deforming the Floor differential on the direct sum by multiplication that comes from the second from U2. Physically, what this says is that the two branes describe giving expectation values to an open strict tachyon at the intersection, one large and one small. The equivalence means that that homes with either the connected sum brane or the cone over P brane are the same for any n. Now, in good situations, one can generate the entire derived category by a sequence of cone maps, direct sums, and degree shifts from a finite set of branes. Now, our theory admits an additional simplification, which is not typically present. Because so far, essentially everything we said is true for any derived Foucault-Seidel category or any equivariant derived Foucault-Seidel category the way I defined it. Since the target of our theory involves symmetric products, our theory turns out to be a close cousin of Heger-Floor theory. The target of Heger-Floor theory is simply a symmetric product of D copies of A. Heger-Floor theory is associated to GL1/1 and also leads to not invariance. It would lead to an Alexander polynomial, which is a close relative of the Jones polynomial we get for SU2 by taking G to be SU2. In particular, when we take G to be SU2, both Y and the target space of Heger-Floor theory involve a single symmetric product. The fact that GL1/1 and SU2 theories are such close relatives has a simple string theory explanation, which we'll see in the last lecture, hopefully. Now, to begin with, recall that a point in the symmetric product is a D tuple of unordered points on the Riemann surface. Now, since Y, this in particular implies that Lagrangians on the target of Heger-Floor theory, which is just the symmetric products, are products of D one-dimensional Lagrangians on the Riemann surface. So this is a picture that you get for, say, D is equal to 2. Okay, so this is not a direct sum of Lagrangians. You think of it as a product of two one-dimensional Lagrangians, which gives a single Lagrangian in the symmetric product. Single two-dimensional Lagrangian in the symmetric product. Correspondingly, the intersection point of a pair of Lagrangians on the target of Heger-Floor theory is a D tuple of intersection points of D one-dimensional Lagrangians on A taken up to permutation. So these two branes, the product of L1 and L1 prime and L2 prime and L1 and L2 intersect over 2 points. One, the orange point, and one, the green point. In Heger-Floor theory, one gets to rephrase the A model in terms of counting of holomorphic curves to a product of, instead of counting holomorphic maps to Y, in terms of counting of holomorphic curves in the product of D, the domain of the Landau-Gisberg model, the worldsheet of the Langlands model times A, the Riemann surface in the target, with a pair of projections, one to D as a default cover and one to A. So that when it falls on A, it falls as a domain with boundaries and one-dimensional Lagrangians. That's known as the cylindrical approach to Floral theory, which was discovered in the context of Hegel-Floral theory. Now, a holomorphic map from a disk to target of Hegel-Floral theory projects with non-negative multiplicity, which is just a symmetric product, with non-negative multiplicity, so domains on the Riemann surface A, with boundaries and one-dimensional Lagrangians and vertices on their intersection points. So this is an image of a holomorphic disk. The cylindrical approach to Floral theory reduces the problem of counting holomorphic maps to Y, the target of Hegel-Floral theory, to well-defined but hard problem in complex analysis, one for each domain A. It essentially amounts to multiple applications of the Riemannian mapping theorem. A simple piece of this is that one can read off from the domain the Maslov index and the equivariant degree of the map to Y. For example, the Maslov index of a disk is given by some simple formula that involves what's called the Euler measure of the domain, involving the Euler characteristic of the domain, the number of acute and obtuse angles, and a term which essentially measures the intersection with of the domain with a diagonal in the symmetric product. That has to do with multiplicities of A at the vertices and so forth. So the above disk has Maslov index 1 in Hegel-Floral theory. In the theory based on Ry, a generic point on the target is a D-tuple of points on the Riemann surface, which are labeled by simple positive roots of G and otherwise identical. This is because we get a product of symmetric products, rank D worth them. Correspondingly, Lagrangians and Y are products of one-dimensional Lagrangians on A, similar to Hegel-Floral theory, except with the Lagrangians are now labeled by simple roots. And the intersection points are intersection points of one-dimensional Lagrangians taken up to permutation, where you only care about the Lagrangians that come from the same symmetric product to intersect. In the cylindrical approach to Floral theory, the cylindrical approach to Floral theory extends to Y because holomorphic maps to Y correspond to holomorphic maps to Y naught, which is just the product of symmetric products, which pull W naught back to a regular function on D. Okay, so in other words, the maps to Y are a restricted subset of maps to symmetric products or product of symmetric products. Those for which W naught restricts to regular, pulls back to a regular function on the domain. Because of this, the maps that the two theories count are different. Well, they're certainly different in general, but they're different even for SU2 case when the target is involves a single symmetric product. So in the closest case corresponding to SU2, the maps that you count correspond to holomorphic curves in D times A, such that the branch points of the projection of S to D as a default cover must map to punctures on A in a specific way, keeping track of multiplicities. So as a result of this restriction, you cut down the moduli space, and the Maslov index of a disk becomes given by a different formula, which is given just in terms of the Euler measure and no contribution from some intersection with the diagonal. So this disk, while it has Maslov index 1 and can contribute to the differential in Hegel-Floral theory, has Maslov index 2 in the theory associated to Conformal homology or SU2. All right, so now the theory turns out to be the theory based on Y, the derived Foucault-Seidel category of Ry with potential W turns out to be solvable exactly. It turns out to be equivalent to a derived category of modules of an ordinary associative algebra, which one can compute. The potential W has critical points, which are isolated and non-degenerate. The theory, the two-dimensional theory, is semi-simple or massive. The critical points are labeled by the weights in the same weight space of the LG representation that conformal blocks transform in. This mirrors the fact that the torus acts on X with isolated fixed points, which get associated to the weights of the Lie algebra via the geometric Satake correspondence. The critical point equations are a variant of the famous Godin type beta ansatz equation from works of Fagin, Frankel, and Reshetikhin. For every critical point of the potential, we get a pair of left and right symbols, which are respectively the set of all initial conditions for upward or downward gradient flows of real part of W, on which imaginary part of W is constant. The soliton equations were gradient flow equations for imaginary part of W, and the real part of W was constant on them. So for the thimbles, we'll do the opposite. The set of thimbles depend on a chamber in equivariant parameter space. There's a choice of chamber in which the left thimbles are simply products of real line Lagrangians on the Riemann surface. So they're always products of Lagrangians on the Riemann surface, but now they're products of real line Lagrangians, lines that just run around the cylinder. This should be reminding you of, say, mirror symmetry for a cylinder, okay, where such branes are particularly nice and they would map to line bundles on the mirror of the cylinder. By results of Seidel, these thimbles generate what mathematicians call the Rav-Fukaya-Seidel category of Y with potential W. The category is also the same category defined by Hori, Iqbal, and Vafa. Here we need to do something. For these non-compact branes, the potential does matter because we use the potential to define them. Moreover, because of non-compactness, one has to take care to define the Helm spaces so that the intersection points don't run off to infinity. And a way to define the Helm spaces so the intersection points run off to infinity is what mathematicians call the Rav-Fukaya-Seidel category. Physically, it just corresponds to instead of taking intersection of thimbles on which real part of W is constant with the thimble on which real part of on which the imaginary part of W is constant, with one on which imaginary part of W times a phase is constant. Okay. These thimbles generate an algebra which inherits a product from Floor theory. That's always true. What's special here is that the algebra turns out to be an ordinary associative algebra that's graded only by equivariant degrees, because all the algebra elements have cohomological degree 0. We can compute those because, as I explained, one knows how to compute Maslov indices of everything in this theory. Now, the fact that all intersection points, all terms in the Floor quotient complex have Maslov degree 0 means that the action of the differential is necessarily trivial because it has nothing to shift them to. So you don't get some DG algebra, or you get an ordinary associative algebra. Now, there are not many holomorphic discounts that one can evaluate explicitly, but it turns out that all the ones that contribute to the algebra products are computable because they come from products of triangles, which are essentially determined by the D = 1 theory. Those are one kinds of maps We know how to count a map, compute the map, how to count maps from a disk with 3 marked points to a homomorphic triangle like this. That's a high school geometry, in which in turn, so the calculation is analogous to what Aru did in the context of Hager-Floyd theory. So the resulting algebra can always be thought of as a path algebra of a quiver, whose nodes correspond to the critical points, where paths from one node to another encode the homes between the branes. For us, these quivers will always have closed loops in contrast with simpler theories coming from single-valued potentials. This gives us a richer representation theory and richer derived category. So, for example, for Y, which was on this equivariant mirror of the resolution of the A-1 surface, the algebra is simply a path algebra of the affine A-1 quiver with relations that are somewhat unfamiliar and which capture where the paths on the quiver capture intersection points between the symbols. So the algebra is simply the path algebra of the quiver, and the relations that capture the relations that you get from the product on Floyd theory. Now, for general Y associated with arbitrary G, not just the case I gave is a very special case of the G being SU2, but in general, the algebra is best represented graphically. One can describe it by starting with a cylinder with M red strands running along it, labeled by highest weights of the representations associated to vertex operator, the representations coloring the knots. The order of the strands is the order of the punctures on the circle in the Riemann surface. In fact, the circle here, S1 in our cylinder, is the circle that comes from the Riemann surface. And the vertical direction is the space direction of the Landau-Ginzburg model. The algebra element is a configuration of strings, which are colored blue, but each is labeled by a choice of a positive simple root of the Lie algebra. The configuration at the bottom is determined by the in symbol, and the configuration at the top by the out. The equivariant degrees are obtained simply by counting intersections. For every intersection of a pair of blue strings, you get what's effectively this kind of contribution. For intersection of red with the blue, you get this. If they intersect, right to left, and if left to right, you get just one. The other equivariant degrees associated mirror to the lambda action capture the winding numbers of strands around the cylinder. The algebra multiplication is simply stacking cylinders. What the relations say is that the blue strings need to be taut, or else the algebra element vanishes. The KRLW algebra of Kovanov, Lauda, Rokwi, and Webster are given in similar terms, but with more generators. The blue strands also allowed to carry dots and with different relations. So these relations, as I've written them, hold for SU2. By result of Webster, which is how he proved that his old construction, or this more novel one involving strands in a cylinder, agrees with the derived category of coherent sheaves. This algebra describes the category of branes on the big X. So the fact that there are more homes between the branes is natural because the big X is more complicated. All right, so I am at this point, okay, I'm pretty much out of time, right? I can say a little bit more, which
you can have a few more minutes if you like.
Okay, sure. There's a few more things I can say. So So this was just the algebra generated by the left symbols, the one that looked like real line Lagrangians. The right symbols are all, they appear compact on the Riemann surface. They are dual to the left in the sense that the right and the left symbols always intersect at a single point if they correspond to the same critical point of W and not at all otherwise. These relations imply that that the right symbol branes are simple modules of the algebra generated by the left symbols. If the left symbol algebra is a path algebra of some quiver, the simple modules are modules, quiver representations of weight 1 for the node that labels the brane and weight 0 for all the others. Once more, applying the theorem of Seidel, we get an equivalence of the derived Fukaya-Seidel category with the derived category of the right modules for the algebra HX, where HX is endomorphism algebra, the algebra of Holmes between the direct sum of all the right symbol branes. In our running example, Y being equivalent to resolution of an A-1 surface singularity, the algebra HX is essentially the algebra studied by Kovanov and Seidel in their famous paper where they initiated connection between A model and representation theory. Now we are seeing many, many more such examples, there being the first, and other than Hegel-Floyd theory, pretty much the only one. The algebraic way to understand this, the fact that derived Fukaya-Seidel category is equivalent to both the category of A modules and the modules of HX, should be causal duality. Because what I told you so far implies that the left symbols are what I call projective modules of the algebra A and simple modules of the algebra HX, and that the right symbols are simple modules of algebra A and indecomposable injectives of HX. This causal duality has many striking algebraic implications. For example, it implies what's called a formality of algebra HX, whose theorems are extremely difficult. These algebraic proofs of which are extremely difficult. So these two algebraic descriptions should make mirror symmetry that relates X and Y manifest. And next time we'll see that we'll explain more about that and homological equivariant mirror symmetry.
Okay, well, thank you very much for your talk. Are there any questions? Okay, here's a question from Pranav Pandit.
Yeah, so my question is about, so yesterday you had this description of Kähler parameters in the B model picture of Kähler moduli space. Is it easy to see, at least at a heuristic level, why, I mean, the A model picture, why that is the space of stability conditions for this category?
Yes, because remember, essentially, yes, the holomorphic form on Y is simply the product of holomorphic forms on the cylinder, which means that the stable branes are just the straight line branes, and a lot of the cone maps come just from the one-dimensional theory. So yes, it should be very easy to see.
Great, thanks.
Okay, there's another question from Aswin and Balasubramanian.
Hi, yeah. So my question is about the statement about causal duality that you mentioned at the end. So I was sort of intrigued by the appearance of Coulomb branches and some causal duality. Is the whole picture related also to symplectic duality?
It is not directly related to symplectic duality. I'll explain the relation to three-dimensional mirror symmetry. But the way I think about it, it's physically, it's strictly different than anything I've seen in the context of symplectic duality. In the paper by Gayotto, Dimofte, and I think Hilburn, I'll forget some others up here, causal duality. They did consider a Landau-Gisberg model, which is a close cousin of the Landau-Gisberg model that I'm writing here, except it's not the same. The parts of it that are different are those terms that have to do with equivariant actions that preserve the homomorphic symplectic form on the big X. And moreover, the way you derive that Landau-Gisberg model from the three-dimensional theory is different from the way you need to get knot invariance and get this story. You're taking strictly a different limit. Their limit was sort of a symmetric limit that treated Coulomb and Higgs branches symmetrically. The limit to get this Landau-Gisberg model, even though the answer looks on the surface of it the same, strictly, as I'll explain, hopefully in tomorrow's lecture, strictly treats Coulomb and Higgs branches asymmetrically. Now, it is possible that one can still, because it's one term, that's the difference, that for questions where that term is not relevant, the two stories just become the same. So for example, if we just wanted to study invariance of knots on R3, those kinds of terms actually just disappear. And by a matter of accident, the two theories will give the same answer.
I see. Okay, thank you.
At the same time, that the target of Y, so you'd be zooming into a small piece of the Riemann surface where you don't see the whole cylinder. Yeah. So in some limits,
Okay, are there any further questions? Okay, if not, then let's thank Mina again.
Great, thank you. Thanks for listening.